Here's a problem. And by the way, our topic for today is called, hopefully you'll actually keep this in mind. It's called inverse variation. By the way, you know what inverse means?
Yeah.
What? Opposite. Okay, good. Keep that word in there. And then as you, inverse variation. Okay, as you work on this problem, I want you to start thinking about the inverse variation in the context of inverse variation, meaning opposite of some sort. So here it is. A rectangle is 36 inches wide and 20 inches long. How wide is a rectangle of equal area, meaning a similar rectangle with the same area, okay? Same area. If its length, the new rectangle, of course, is 90 inches long. Okay, so go ahead and work on that for a couple minutes, and then we'll find out what you have. Go ahead. So, what did you find out about the second rectangle?
It's 8.
It's 8. Oh, how do you get that? What do you do? Oh, wait. You're giving me like a different number now. 720? How do you get 720 to begin with? Okay. All right. Slow down. I need you to explain it to me.
Okay.
How do you get 720 again?
From the first
Okay, so you're saying that you get 720 from the first rectangle.
Yeah.
So first rectangle is basically 36 by 20, right? So area, we're still using the area formula of rectangle, which is what? Length times width. Great. Okay, so length times width, 36 times 20, you get 720. This is the area of the first rectangle, right?
Uh-huh.
The second rectangle, you said, is going to be very long, 90 inches in length. What do you notice about if the length is being lengthened? Then what happened to the width? It gets smaller. Why does it have to get smaller? What happens if the length gets longer and the width gets longer too?
The area will
The area gets bigger. So what is actually holding in place here? What is the boundary basically? What's the limitation? What is holding your rectangle in its, what is it? 8? I know. Think about this. What I'm asking is, why do you need to adjust the width based on the length? Because of what? Because of the area. Area is staying what throughout the process? The same. Okay, I want you to hold that word here. The same, right? So because it has to stay the same, if you're going to be lengthening one side, the other one has to be shorter. Think about that. If it stays the same, the area will be bigger, isn't it? Think about that, right? If, for example, if I keep this 20 and lengthen the length here, what will happen to the area? Will it stay at 720? No. So something has to give if the other one gains. Is that true? Compensate. So here, we found that for the width and this length, for this combination to make 720 as an area, it has to be exactly 8. And how did you get that 8 again? Okay, so you're taking the area divided by 90, right? And that is the width, which is 8. But what you're actually doing there is basically solving for W. Is that true?
Yeah.
And you know that to solve for W, you divide both sides by L, and so W is area divided by L. What if I ask you to find the length? Then what would happen then? Divided by W instead. But notice that we always start with what's being the same throughout the problem. In this case, the area is being the same, so we just have to divide it. So are there any questions on this problem so far? Now, can you tell me, can we have another combination of this? Is this the only combination that you have to make 720? Can you give me another combination of length and width? Beside 36 and 20, beside 90 and 8. Do we have another one? Yes, right. Huh? 720 and 1. You can have like the longest length, 720, and the width just a little 1. That's 720, right? What else? Can we have another one? What is it? 120 and 6. That works. 720, right? Any other combinations?
80 and 9.
80 and 9. Yeah. So you can sit here and just basically all day long tell me different combinations. So with that, I just kind of I came up with a chart here to show you the relationship between length and width having the same exact area. So let's take a look at this right here. Here it is. Look at this. Starting with the length of 1, then the width has to be 720, right? Because if you want to make the area 720, that has to be the case. It's the product of the length and the width. Look at the second case. I can have I have the length to be 2 and 360. 3 and 240, 4 and 180, 5 and 144, 6 and 120, like what Diana just mentioned earlier. But what he knows about the relationship between the length and the width. As the length increases, what will happen to the width? What do you see?
Decrease.
What is it? Decrease. So they are having the opposite effect, right? Remember our lessons today? What is it about? Inverse variation. So it means this is what our theme is. If something is going to be increasing, the other one has to be decreasing. Is that clear? But notice, whether something is increasing or decreasing, you still have the same exact area. It stays the same. So instead of using the term same here, we're using the term constant of variation. Constant means the same. Okay? So just keep that in mind. I want to show another piece of work here. It's a graph. So here, take a look at this. If I can bring this up. Where is the graph? There it is. Okay. So let's take a look at this graph. Let's use it in the context of the area again. We know that area is length times width, right? But because I want to put this on a graph, use what axis here? X and Y. So can I just say that for the length, can I link this side, right?
Yeah.
So can I use X for that?
Yes.
And for the width, can I use Y?
Yeah.
So the area is basically X times Y. Is that okay? What is the area that we want to find again? How big is the area?
740.
720. So 720 equals to X times Y. And
Put 700.
oh, wow. I'm dyslexic. I'm sorry.
You are?
No, I'm just kidding. Mistakes happen. Okay, but because we want a graph, we want to solve for Y because Y equals to whatever, right? So how do we solve for Y? Divided by X. So I put that. It's just I need to put in a certain format for the graph to work. So Y is 720 divided by X. That's what I want to input into here. So watch what happens when I want to input that equation into this function. Y equals to 720 divided by X. So let's kind of zoom in to show you that I just inserted that there. So I'm going to hit enter and it's going to graph for me. You don't see anything yet. Let me zoom out. Here it is. Ooh.
What the heck?
I know it's weird, right? But look, it has the negative side, it has the positive side. Which side can I pick for this problem? Why?
Because it's a rectangle.
Right. We're talking about the length and the width of a rectangle. Okay, and remember the X side here is the length, right? And the Y here is the width. So watch what happened. If I go this way, that means I increase the length. What's happening when I increase the length?
Decrease.
You see it's decreasing the width. Versus if I increase, or walk this way, if I decrease the length, what's happening to the width? It increases, and that's what you see in the Excel chart. You see it? I hope you see that relationship. This is called inverse relationship. So for all of the inverse variation graph, that's what you expect to see. Something increases, the other one has to decrease. If the other one decreases, the other one has to be increased. I'm sorry. It's opposite relationship. That's what I want you to understand from this. All right, with that in mind, let's take a look at another problem and see if we can actually figure this out. There. So now, here's another context that I want you to use. It's a traveling problem. The Zelinski's family can drive the 220 miles to their cabin in 4 hours at 55 miles per hour. Now, their son all of a sudden claims that, hey, you know what, I don't want to spend 4 hours on the road. I want to cut half an hour out of that. So about 3.5 hours, right? 3.5 hours. If they can actually drive at 65 miles per hour. So if you increase the speed, is it logical? If you increase the speed, are you going to cut down the time on the road?
Yeah.
Okay. You see the relationship again?
Yeah.
If you increase the speed, the time on the road will be less. So what kind of relationship is that? Inverse relationship. Okay. Now, I want you to verify if Jeff's claim is true. Is it true that if you, by number, of course, don't just say yeah, it's true, but I want you to really verify that if they indeed drive at 65 miles an hour, their driving time will cut in half. Cut instead of 4 hours, it'll be 3.5 hours. How do you verify that? What do you have to use?
As miles per hour increases, the time decreases.
Well, we know that. We want an exact value though. Can we verify? What do you have to use here in this case? Just like the other one, we use area equal length times width. This is about distance times and speed problem. What do you have to use? Velocity. Well, did we learn something about that before?
D equals R.
What is it?
D
What?
equals R.
TRT, very good. Distance equal rate times time. Did you learn that?
Yeah.
In science too, right? We're talking about distance equal rate times time. How fast you drive based on how long you drive will give you your total distance. Well, let's verify the first claim. It says that if you drive at 55 miles an hour for 4 hours, you will cover 220 miles. Let's see if that's correct. What are you plugging to here for R?
4. Wait, 4, yeah. No, no.
55 miles per hour. What about T?
4.
4. Let's multiply that. What's 55 times 4?
220.
220, so it's correct. That at 55 miles per hour for 4 hours, you will cover 220 miles. Now let's verify Jeff's claim. Jeff now said that if you drive, we're still using the same exact formula. If you drive at what speed?
65.
So what do you replace that with? Replace that by the rate. So 65, and what about distance? Do we have distance?
Yeah.
What is
220.
it? Oh, why are you using the same value?
Because it's always the same.
Huh?
Because they're both going
at the same place.
Same place, very good. So if you're going to, for example, from your house to your friend's house, it's always going to be the same distance, right? It's not going to change unless we have like a catastrophe or something. Something really bad happens, you know? But not the case, we're talking about a normal case. So there we go, the distance stays the same. Oh look, distance stays the same. Just like our area problem, which has the area stays the same. What can change though in this case?
Time.
The time and the
Rate.
the speed, right? The rate. Very good. So let's verify to see if it's correct. 65 times t equals 220. How do you solve for t?
Divide.
Divide it. So we divide both sides by 65. What is t? What do you think? 220 divided by 65.
4.
So you actually divide that.
4.
4.
4?
No.
Wait, no.
3 point what?
3.5.
Ah, roughly. Very good. So, is this claim true?
Yes.
Did we indeed cut about half an hour off of our traveling time?
Yes.
Indeed, because one side is half an hour, right? So, Jeff's claim is true, that we cut about half an hour off of our driving time. Okay, now, here's another challenge for you. What if I want to cut that in half? The traveling time, not half an hour, but I'm talking like in half. Instead of 4 hours, I just want to get there in 2 hours. So, how fast do you think this family has have to drive? Basically?
110.
Just do it.
8.
Show me. Ooh, how do you get that, by the way? Since you're like,
Divided by.
Oh, that's messed up.
okay, fine. And he's right. Okay, thank you for swallowing. That's fine. Look, is it still the same distance?
Yeah.
I mean, I still need to drive 220 miles, right? But this time around, for RT, the T I know, right? What is it I want this time? Just 2 hours, so I can replace that T with 2 hours, and if I want to solve for R, what do we need to do?
Divide.
Divide it.
Was he sleepwalking?
R is
110.
110. 110 what? Miles per hour.
Oh, yeah.
Okay. So, is that legal?
No.
No. But yes,
Yes.
you certainly get there faster by speeding up, right?
It's legal.
But what did you see here? Once again,
A butt.
let's step back a little bit and observe. The higher speed you go,
The time
Okay,
the
guys.
less time you be spending on the road. The slower speed you go,
the more time you
the more time you spend on the road. And that has an inverse effect, and this is why we call it inverse variation. But listen carefully. I want you to go and observe a little bit here. So the very first problem that we did involving the rectangle and all the way to what we do with the distance problem. What stays the same throughout?
The
The
far
far
distance.
distance.
Okay, the distance in the distance problem stays the same. What about the shape problem?
720.
The area stays the same, right?
Yeah.
So let me just go ahead and go back here and show you. First case, I have area equal length times width. Second case that I gave you is talks about distance equal r times t. Ah, oops.
Uh-oh. What's that?
Wow.
R times t. Okay, now, what's similar is this, that the area stays the same. So I'm just going to use the word constant in that place. And the distance in this case stays the same in both problems, right? You notice that in the first problem, the L and W, do they stay the same throughout?
They either go
No.
up or down.
Oh, they either go up or down. So if one goes up, the other one has to go
Down.
down. So that means these two values can change. Is that true? Just like our rate and time problem. What do you notice? What's happening to the rate if the times goes down, for example?
It goes up.
Goes up.
So, do you see the similarity between this problem to the last?
Mhm.
So this can change once again. But if you actually have to compare both cases, if you take two values that can change and multiply them, you always get back the constant value. You see it? So, if I have to sum up everything here, because we want to have like a universal formula to use in any context. This is only for area. This is only for distance. We want to have something that can be used in any case, so therefore I have to come up with different variables, and I'll show you what it looks like. For the constant, I'm just going to define a universal letter K to represent a constant. In this case, we call this the constant of variation. Okay, remember? That value stays the same. And here, instead of using L or W or R and T, I'm just going to use our generic variable that we always use and use to graph all the time, which is X and Y. So this here, notice it still reflects the same exact kind of relationship. Constant is X times Y. And notice that when we graph, isn't it true that X and Y can change?
Mhm.
There it is. So here is what will stay constant. X and Y, of course, can change. But they need to be opposite of each other, inverse of each other. If one goes up, the other one has to go down. Okay? And vice versa. For example, if I want to solve for X, well, what happened? What do I need to do? Divided by Y, right? So is it going to be K over Y? And the other one, if I want to solve for Y, what happened to the X? K over X. So from one formula, I can certainly write two others based on that same fact. Any questions so far on the constant variations? You see the similarity between two cases? I'm just telling you that, hey, this is just a broad view of the whole thing. Instead of being specific on area or distance, it's going to be applied to any case. K is X times Y. And you can certainly replace, oh yeah, X could be the length, Y could be the width, and K could be the area. Or, in this case, X could be the rate, Y could be the time, and K could be the distance. You see it? It's like it's just a general view of the whole thing. Questions on that? Alright, now that we understand at least the concept, variation kind of concept, let's take a look at this problem. Students at Roosevelt High School are collecting canned goods for a local food pantry. They plan to distribute flyers to homes in the community asking for donations. Last year, so let's compare. This is last year. They have how many students? 12 students. And what are they doing? They're distributing flyers, right? In how long? How long did they 9 hours. So last year they spent 9 hours, 12 students spent 9 hours last year to distribute flyers. This year, they have extra help. How many students are
15.
present this year? 15 students. And I asked you to figure out how many hours will they spend now to distribute the same amount of flyers.
So,
Okay, so good guess, but listen carefully. First of all, do we have a constant variation defined yet?
No.
Okay. For those of you who jump in right in and say, oh yeah, we do, it's 1,000, it's stayed constant throughout the last year and both year. Be very careful on that. Let's just read and go back to what I cover about constant variation. How do we find constant variation again? It's what can change, multiply together to get you the constant variation, right? So you go back to the same problem and see, wait, what's changing? The number of students can change, and the hour can change. The more students you have, the less hours. You see the opposite relationship? Just like how x and y is. So if you call this is like your x and this is like your y, how do you find k?
Divide.
Yes. How do you find k?
Divide.
Multiply.
Okay, let's go back again.
Divide.
If I have your x and y, how do I find k?
Divide.
If I have x and y, how do I
Multiply.
find k? Just like if I have the length and width, how do you find the area?
So you got the other one with that.
If you find one or the other,
Okay.
that can, okay, so be very careful, okay? If you are confused, a bit confused, just go back to your area problem. Is it true that the number of students can change over time?
Yes.
Is it true that the number of hours can change based on the number of students?
Yes.
That's true too. So these are the changing values, right? And we give you a very basic definition of the constant of variations. To find a k, or constant variation, we just have to multiply or get the product of the value that changed. In this case, the students and the hours. So if you take the student times the hour, what do you have? 108. Student hours, right? What it means is this. I hope I can clarify it clear for you. 12 students, if each student put in 9 hours, is it true that they put a total of 108 hours? Because if you're going to be spending 9 hours on each of you, you're putting in together, I know, you just spend one day, 9 hours. But if you count each one individually, that's 9 hours per student. You have 12 students. That's 108 hours. This right here now is called your constant of variation. Now that you have your constant of variations, how does this help you figure out what goes in here?
Divide 15.
There it is.
Yep.
Oh, you mean like 108 by 15?
Yes.
Be careful when you say that. There it is. That's how it is. Just like exactly like, oh, this is my first rectangle, this is my second rectangle kind of deal. Same case. So then you write 108 divided by 15. Constant variation divided by whatever that's given here. So what is 108 divided by 15?
8.
Do it. You have an answer yet? 7 what?
Hours.
No.
Student.
You can actually get a terminating decimal. What is it? 7.2. Yeah, I got people to get 7 hours before. Pretty good. That's a good guess. 7.2 hours.
Yeah. Okay.
Okay. Good. 7.2 hours. Does it make sense? More people, less time. That makes sense because you got a lot more people distributing the same amount of flyers. So there it is. So before we end this day, for the quiz anyway, not the quiz yet. I have this for you to work on. Try this now. It's a very generic problem. Go ahead.
If y equals
If y equal to 12 when x equal to 5, find y when x is 3. Think of this as your first case. This is your second case. Like first area, second area. How like this? So go ahead. I want you to find out what y is.
20.
Okay. Jeez. Okay, fine. What is it?
20.
How do you get that? What is wait. What is the constant of variation here?
60.
How do you get 60?
12 times 5.
Right, see? This can change, this can change. 2 change, multiply together, will give you a constant variation of 60. And once we get 60, we just divide it into the other one, right? And that's how you get 20. Any question on that? Okay, fine.
I say that.
Fair enough. We're done. Let's do the quiz.
I was gonna